Okay, today we're going to do the Pythagorean theorem. You have done Pythagorean theorem before in pre-algebra. We're just going to take it up a little bit from what you did in pre-algebra. We're going to simplify our answer rather than just leave it or give a decimal approximation. And we're also going to look at the converse. How can we turn this around? Okay, which I think you also probably looked at in pre-algebra, but maybe not. It depends. So the Pythagorean theorem says this: in a right triangle with sides of A, B, and C, where C is the longest side, which is called the hypotenuse, which you already know because we did hypotenuse leg in the last unit, that A squared plus B squared equals C squared. Okay. Now, most adults, if you were to ask them what's the Pythagorean theorem, an awful lot of them actually can, after they think for a minute, they're like, oh, that's A squared plus B squared equals C squared, which is true. But then if you ask them, well, what do A, B, and C stand for? They're going to most likely kind of go, I don't really remember. They remember the equation, but not what it's good for. So that's important, though. It has to be a right triangle. If it's not a right triangle, the Pythagorean theorem does not apply. Okay, now, in a couple of years, when you take pre-cal, you'll learn some other things that do apply when you have something that's not a right triangle. It's called the law of cosines, and you'll learn it, like I said, in pre-cal, and it's great for things that aren't right triangles. It's kind of like the Pythagorean theorem with an extra piece stuck on to fix the non-right triangle bit of it, okay? But for now, we just have this. So let's solve some of these. And like I said a moment ago, instead of just leaving your answer as an unsimplified square root or giving a decimal approximation for it, we are going to simplify the square root. That's why we learned that yesterday. So let's take a look. In every case, the first thing I always do is identify where the hypotenuse is. The hypotenuse is always opposite the right angle. So in this case, the hypotenuse is x. That's the one that goes by itself in the Pythagorean theorem. So the sum of the other two sides squared, 10 squared, plus 14 squared, is going to be equal to x squared. So 10 squared, everybody knows that one. It's 100. Who knows 14 squared?
196.
196. Thank you, sir. It's helpful to know those. Is equal to x squared. So that would be 296 is equal to x squared. Well, we don't want x squared. We want the length of that side that has a value of x. Well, how do you undo something squared? Take the square root. So x is the square root of 296. And now we're going to simplify that square root. Most people on this one would probably do prime factorization. It's not immediately obvious what the biggest square root that would, perfect square that would divide evenly into this, but I'll start with 2. That's 1, 2 goes into 9, 4 times with 1 left over, and 2 into 16 is 8. I'll keep using 2 until I can't use it anymore. 2 into 14 is 7. 2 into 8 is 4. I can divide by 2 again. 2 into 7 is 3 with 1 left over. 2 into 14 is 7. Well, now I've got 37, and you're like, I don't know that number. Okay. What's a perfect square that's near 37? 36. What's the square root of 36? 6. You only need to check prime numbers that are smaller than 6. That's not very many. I need to check 2, 3, and 5. Does 2 divide evenly into 37? No. Does 3 divide evenly into 37? Nope. Does 5? Then this is a prime number. So I've got the square root of 2 times the square root of 2. I'm going to group those two together. And then I've got a square root of 2 that doesn't have a like partner. The square root of 37, I'm going to group those two together. That's 2 square roots of 37 times 2. And you're like, do I have to multiply that out? Well, I already have it right here. It's 74. You don't have to turn around and multiply it back out. You've already done it. So x is 2 square roots of 74. Okay, any questions about that? All right, let's try this one again. Always start by figuring out which side is the hypotenuse. In this case, again, it's x. So I'm going to have 5 squared plus 12 squared is equal to x squared. So it's 25 plus 144 is x squared. Add those two together, that's 169 is x squared. That's really way too close together. So x is the square root of 169, which is what? 13. This is an example of something that's called a Pythagorean triple. Pythagorean triples are a set of 3 numbers that work in the Pythagorean theorem. So 5, 12, 13 is one of them. And from here on, if you have a triangle where you know the legs are 5 and 12, you don't have to show me any work. If you have this memorized, you can just write down 13 and move on to the next problem. Likewise, if the hypotenuse is 13 and one of the legs is 12, the other leg has to be 5. No work needs to be shown. Write down 5, go on to the next problem. So knowing these can make your life easier because it makes doing problems faster. I'm going to tell you 2 other ones. The simplest one is 3, 4, 5. It's the only one where it's consecutive numbers. 3, 4, 5. That makes a right triangle every time. And this one doesn't show up nearly as much, but 8, 15, 17 is another one.
So if we have like those 3, you just find the one that's missing and put it in?
Yes, as long as the biggest side is the hypotenuse.
Okay.
Right? So if the hypotenuse was 15 and one of the legs was 8, the other leg's not going to be 17. Right? You do have to be careful of that. But yeah, these come up on standardized tests fairly regularly. Not as regularly as they used to, honestly, but pretty regularly. Like on the SAT, ACT, all those alphabet soup tests. It shows up. And you're like, but they let you use a calculator, so what's the big deal? Well, it's a timed test, right? If you can do it faster, would that be better? Would that give you more time for other questions that are harder? Yeah. So I think it's worthwhile memorizing these. Especially the 3, 4, 5, and 8, and 5, 12, 13. 8, 15, 17, it doesn't show up as much. But those other 2 show up quite a lot, actually. All right. Well, let's do some where it doesn't work out quite the same way. where the hypotenuse is not what we're looking for. Here, the hypotenuse is 16. So I'm going to square the other two sides. 12 squared plus x squared is equal to the hypotenuse squared is equal to 16 squared. So that's going to be 144 plus x squared. Who besides Morrissey knows 16 squared? He seems to know an awful lot of them. Yes?
256.
Very nice. 256. So now we'll subtract the 144 from both sides. We get x squared is 112, if I've done the arithmetic correctly. So x is the square root of 112. And now we'll try and simplify that. If you're doing it by prime factors, the most obvious thing I think is that it's divisible by 2. 2 goes into 11 5 times with 1 left over. 2 goes into 12 6 times. 2 goes into 5 twice with 1 left over. 2 goes into 16 8 times. 2 goes into 28 14 times. 2 goes into 14 7 times. And 7 goes into 7 once. So we've got now x is the square root of 2 times the square root of 2. I'll group those two together. And then another square root of 2 times the square root of 2. I'll group those two together. And a square root of 7 still left. So that's 2 times 2 times the square root of 7 is 4 square roots of 7. All right, let's set this one up. Where is the hypotenuse? Which side is the hypotenuse? 10 is the hypotenuse, so that's the one that goes by itself. So it'll be x squared plus 6 squared is equal to 10 squared. So that's x squared plus 36 is equal to 100. Subtract the 36 from both sides. X squared is equal to 64. So x is the square root of 64, which is what? 8. Oh, this is another Pythagorean triple. And you may be going, Mr. Davis, why didn't you tell us about this one? Well, I kind of did. I told you about 3, 4, 5, right? This is 3, 4, 5 doubled. 6, 8, 10. So if it was tripled, if I had, you don't need to write this down, but if this was 9 and this was 15, this would be 12. Okay? So you can double, triple, quadruple, quintuple, whatever. Multiply times 10. So knowing those triples and their multiples can save you some time. All right, page 2. So we know how to tell whether a triangle is acute, right, or obtuse based on its angles. We've done that a couple of times. We can also find out if a triangle is acute, right, or obtuse based on its sides. You're like, wait a minute, isn't it the angles that are important? Well, it is. Here's the deal. Don't worry about reading this just yet. Just watch for a second, if you would, please. Let's say I've got a right triangle like this. Okay? And I'll call these two sides A and B and the hypotenuse C. Everybody good with that so far? Okay. What would happen in this triangle if I left A and B as the same length that they are right now, but I was able to make C longer? What would happen to that right angle?
It would become obtuse.
It would become obtuse. It would get bigger, wouldn't it? So if C got bigger, it would start looking more like this, right? What if C got smaller? It would become an acute triangle. So, if in a right triangle we know that C squared is equal to A squared plus B squared, here, this new C would be bigger, squared would be bigger than A squared plus B squared. So, in a triangle with sides of length A, B, and C, where C is the longest side, that's important here, there are three possibilities. First, if C squared is equal to A squared plus B squared, well, that's the Pythagorean theorem. It must be a right triangle. If C squared is greater than A squared plus B squared, the triangle is now obtuse. We've made this side bigger, made this angle bigger. And if C squared is less than A squared plus B squared, the triangle is an acute triangle. I had a student who years ago called this the Goldilocks theorem. For those of you who are familiar with it, when Goldilocks went to the first chair, it was too small. Or it was too big. And then she found one that was just right. And they thought that was hilarious, that it was right used two different ways. And I was like, okay, if that helps you remember, great. Okay, if the big side is too small, it's an acute triangle. If the big side is too big, it's an obtuse triangle. If the big side is just right, it's a right triangle. All right, let's do some examples of that. So, given the sides of a triangle, determine if the triangle is acute, right, or obtuse. Step one is always figure out which side is the biggest side. Sometimes it's pretty easy. What side's the biggest side? 13. So I'm going to do 13 squared, and I'm going to put a question mark because I don't know whether it's bigger or smaller or equal to the other two squared and added together. So 8 squared plus 11 squared. This is another reason to know perfect squares. 13 squared is? 169. I'm going to leave this question mark because I still don't know yet. 8 squared is? 64. 11 squared? 121. Let's see, that's 169 still. This is 185. Is the big side too big or too small? Too small. So this is an acute triangle. All right. Works great as long as you pick out the biggest side first. All right, what's the biggest side for this one? 14. So I'm going to compare 14 squared. So again, I put a question mark here because I don't know what's going to happen yet. To 6 squared plus 9 squared. 14 squared. 196. I always remember that because this one's 169 and that's 196. And they're right next to one another. Compared to 6 squared, 36, 9 squared, 81. That's 196. This is 117. Big side's too big, so this is obtuse. Next one's a little bit harder because it's not immediately obvious which one is the biggest side. But yes,
and 5 are prime numbers.
Right.
So would it just be 11 and 5?
Well, I need the biggest side. Which side is the biggest side? No? Yes?
Oh, you have to square all of them?
No?
You don't?
No? You can. I think it's a waste of time, but you can. How about, what is 4 the square root of?
16.
Oh, yeah.
Which one is the biggest side?
4.
4. Because it's the square root of 16. The square root of 16 is bigger than the square root of 11. So I'm going to compare 4 squared to the square root of 5 squared plus the square root of 11 squared. 4 squared is 16. What's the square root of 5 squared?
5.
5. And the square root of 11 squared? It's 11. So this is a right triangle. Everybody try the last one on your own, please. Pardon? Okay. Yeah, I'll give everybody a couple minutes to get that done. And I'll ask you how to do it, not just what the answer is, okay? All right, Cole, tell us how you set this up.
I didn't really set up. I just
Okay, tell me about that.
so it's double. So it's 3, 4, 5, 6, 8.
3, 4, 5 doubled wouldn't be 6, 8, 12.
Oh, that's not it. I'm
Okay,
12 is obviously the biggest one.
right.
So you do 12 squared is, 12 squared question mark, 6 squared plus 8 squared.
Yeah. So 12 squared is?
12 squared is 144.
Right,
Question mark, 6 squared is 36.
right.
8 squared is 64. So 144 question mark, 100. And it is bigger. So it's obtuse.
So this is an obtuse triangle. Now, Cole, you could use the Pythagorean triple. 3, 4, 5 doubled would be 6, 8, 10, right? Big side's too big. It's an obtuse triangle. You could do it that way, and I would take it. But I'll expect to see some sort of work on all these. All right, I have a worksheet for you. This whole unit is going to be nothing but worksheets.